All right, this is a video talking about solving systems of linear equations. So I want to start off by talking about two lines, which you're familiar with. And when we talk about solving a system involving two lines, so two equations and two unknowns, first there's two ways to solve that system, one being substitution and the other being an elimination. You're going to see I'm going to use elimination here. Very rarely do I actually use substitution, but getting ahead of ourselves a little bit. So talking about lines. Well, two lines, they could intersect in a point, or they could not intersect, so no intersection. And if that's the case, if you remember, that means they're parallel. Or the third situation that occurred when you were solving a system involving two lines was they're the same line or coinciding lines. And when that was the case, back in maybe 6th, 7th, or 8th grade, you would say, same line, infinite solutions. Well, we're going to get a little bit more sophisticated here. So if you go to, let's do an example. And we'll do the example, actually one from the worksheet 2.6. If we do number 5, which is find the intersection of 2x minus y equals 3 and 6x minus 3y equals 9. All right, so when I'm looking at this, I'm probably going to do elimination. And maybe to do that, I would multiply this first equation by -3 if I want to eliminate. Particularly, I was looking at eliminating the y's. So when I do that, I get -6x plus 3y equals -9. And I'm going to add that to the second equation. And I notice, okay, x's are canceling, y's are canceling, and the constants are canceling. So I'm left with 0 equals 0, which is true. If I was left with a false statement, there'd be no intersection, but I'm left with a true statement, meaning all points on these two lines work, and they happen to be the same line. How do I know, kind of looking back, how could I have known they're the same line? Well, this one here is in its most reduced form. But this line, I could divide everything by 3, and I would get 2x minus y equals 3, which, it's actually the same line as the first one. So going back to what I say in terms of my solution, I'm going to say same line or coinciding lines, but it's not all points in space. It's not all points in the XY coordinate plane. They have a relationship between each other. And to figure out that relationship, I'm just going to solve for one variable in terms of the other. So if I solve for y here, I get 2x minus 3. And then we're going to say, we're going to choose a generic variable. And usually that variable is we use k because it doesn't stand for something else, like m stands for slope in math. So we're going to use k, and it makes sense here for me to have x be k, because if x is k, then y is just 2k minus 3. So this is the relationship between x and y, all the points on the line, they have this relationship. If y is k, then x is 2k minus 3. Could I instead have decided, you know what, I want to solve for x and write it in terms of y? Sure. So 2x equals y plus 3. X is y plus 3 over 2. And in that case, I would have had y be my k. Oh, geez, I just realized I wrote this other one wrong. Let's go back here. Sorry about that. I was speaking right, but writing it wrong. X was k. And so y was 2k minus 3. Where in this new situation here, where I solve for x, I'd have my y be k. And then x would be k plus 3 over 2. Both of those are totally acceptable. It's the same relationship between x and y. It just, you're choosing one to be k versus the other. Okay, so now let's talk about again, let's talk about planes, which is going to be it's a linear system because every variable is raised to the first power, and we're going to be dealing with 3 equations and 3 unknowns. So let's first talk about what we might expect with 3 planes. So with 3 planes, what could happen is they could all be parallel. So let's talk about when there's no intersection. So again, we're talking about all 3 intersecting when we're solving a system of 3 planes. No intersection could be they're all parallel, but it could also be that 2 are parallel. Because if 2 are parallel, there's no way those 2 are intersecting, so there's no way all 3 are intersecting. And the third way is none of them are parallel, but in such a way, like if you were to think of kind of a triangle formation where every 2 intersects in a line, but there's no place where all 3 intersect. So I'm going to call that the triangle situation. Okay, so no intersection could happen. They could all be the same plane, so coinciding planes or same planes. And the last 2 situations are, if we think about a room and 3 planes intersecting, we could think about a corner intersecting in a point. You're going to see that's when things are nice. Or we can think of like the binding of a book almost, like so 3 planes intersecting in a line. So that's going to be much more interesting. So those are the possibilities. All right, so let's talk about how to approach solving these. So let's turn to a problem in 2.6. Let's do, I believe it is 6D. Yeah, let's look at 6D and let's do this one together. So this is 6D. So we've got 8x plus y minus z equals 46. Then 3x plus 4y minus 2z equals 27. Then we have 4x minus y plus z equals 14. Okay, big numbers on the right here. So the strategy is always going to, first let's take 2 equations and eliminate a variable. And it's looking like, and I always really scope out what is the easiest to do. And it looks like taking 1 and 3 might be the easiest to do. So if I take 1 and 3, again, the goal is to eliminate 1 variable here. And the reason I picked these 2 is I don't have to do, oops, I want to change that to minus y. I don't have to do anything to actually eliminate, because when I add these as is, notice z is going away. So I've got 12x, oh, and the y's go away too, conveniently, equals 60. So x is 5. Well, that worked out nicely, because oftentimes we'll just eliminate 1 variable and then we have to take another 2 sets of equations and eliminate another. But in that case, we didn't have to do that. Okay, so x equals 5. All right, so let's, I worked with 1 and 3, so maybe let's work with 2 and 3, or even 1 and 2 actually. Maybe we work with 1 and 2. So we know x is 5, so let's plug in 5 for x and 1. So if x is 5, I've got 40 plus y minus z equals 46. Or in other words, I have y minus z equals 6. And so that was plugging into equation 1. And if I plug 5 into now equation 2, I've got 15 plus 4y minus 2z equals 27. Or 4y minus 2z equals, if I subtract 15 here, I get 12. Okay, and actually let's make this even nicer. Looking at this equation here, I can reduce it by dividing by 2. So 2y minus z equals 6. All All right, so now we are working with these two equations in terms of y and z, and let's use elimination to find, let's eliminate z. So if I multiply this second equation by -1, so I'd have y minus z equals 6 from that first equation, then I'd have -2y plus z equals -6. And let's cancel out the z's, and I get -y equals 0 or y equals 0. Okay, good. I'm going to circle that. And now, remember, y minus z equals 6, so 0 minus z equals 6, or z equals -6. All right, so I've got my 3 coordinates. It happened to be that these 3 planes intersected in the point 5, 0, -6. Okay, so let's do another problem because that one just happened to turn out that we got this nice point. But let's see what happens if it's not so nice. So let's go on to 6e. Okay, so in 6e, woo-wee. Okay, so 6e, here's the system. We've got x plus y minus z equals 11, 3x minus 2y plus 2z equals 3, and then 5x plus 3y minus 3z equals 43. Okay. So the strategy for all of these is to pick 2 equations, eliminate a variable, and pick another combination of 2 equations, eliminate the same variable. So let's see what looks nice. Maybe let's just work with 1 and, gosh, what do I want to work with? 1 and, maybe 1 and 2 and eliminate y, I guess. So if I work with equation 1 and 2, then I'm going to multiply 1 by 2. So I'd get 2x plus 2y minus 2z equals 22. And then the second equation is just 3x minus 2y plus 2z equals 3. And wow, this is nice. So I noticed that both x's and y's go away. So I've got 5x equals 25, or x is 5. Okay, so maybe this is going to be a point. All right, so I worked with 1 and 2 here. So maybe I'll plug in x being 5 and work with, maybe let's work with 1 and 3. Okay, so if I plug in x is 5, I've got, for equation 1, I've got 5 plus y minus z equals 11, or y minus z equals 6. And if I put it in for equation 3, I've got 25 plus 3y minus 3z equals 43, or 3y minus 3z equals, let's see, 15, 18. But if I divide by 3, I get y minus z equals 6. Okay, well, notice if I'm working with these 2 equations to solve the system, well, they're the same thing. So if you try to eliminate, you just get 0 equals 0. So that clues me in here that, this system is, these 3 planes are intersecting in a line. And this here is the relationship between y and z. So y equals z plus 6. So if I'm going to go about writing this point, I've got x is always 5 on this line, but I'm going to have z be my k. And so then y is going to be, according to this equation here, k plus 6. So that's the representation of my line. It's all lines such that this is the relationship between the 3 coordinates. Okay, so let's see. I feel like we should do another. Let's do H here, 6H in our sheet. That will be it, just to get a feel of what's happening here. So H is the following. So we've got A, so now we're going away from X, Y, and Z. Same idea though. You can, if you prefer using X, Y, and Z, feel free. Plus 3C equals 14. And then the third equation is 2A plus 5B plus 8C equals 36. Oof, that's an 8. All right, that does not look too pretty. Plus 8C. Okay, so strategy always is to start, pick two equations, eliminate a variable, pick another two, eliminate a variable. Well, I mean, I notice I've got A and 1 and 2, so let's eliminate A. I'm going to multiply the first equation by -1. So I've got -A minus B minus C equals -6, and I'm going to add that to the second equation. And when I do that, I get 8 equals 2C. All right, B plus 2C equals 8. All right. And let's take another combination of 2. Maybe, and again, we have to eliminate the same variable, which is A. So maybe let's work with these two babies. So if I multiply the first equation by -2, I'm going to get -2A minus 4B minus 6C equals -28. And then add that to the third. And A's go away, which I wanted. And I get B plus 2C equals 8. Oh boy, here we go again. So we've got this situation where I'm ending up with the same thing. So if I'm trying to find the intersection of these two equations, two unknowns, I'd get 0 equals 0. So this system is again intersecting in a line. So when this happens, we want to solve for one variable in terms of the other. And okay, so instead of X, Y, Z, we've got A, B, C. And because I solved for it in this way, I'm going to have C be K, and that makes B -2K plus 8. Now, in order to find A, just pick any of the initial equations of planes and plug in for B and C and solve for A in terms of K. So I've got, if I'm going to use number 1, A plus, well, B is -2K plus 8. C is K equals 6. So A minus K plus 8 equals 6. So A is going to be K minus 2. All right, so that's my last piece. So they intersect in a line such that this is the relationship between the three variables. So that kind of gives you a gist of the intersection of three planes and versus the intersection of two lines. So hopefully that's helpful.